Okay, this one can be broken into a bunch of different parts. I have a wrecking ball that starts at rest, V01 equals 0, and falls halfway down in a time of T1 equals 1.2 seconds. But then it continues the journey from this point. Notice I've got two colors there, because this is both the first part and the second part of the problem. In other words, the final speed in the first part, where the red circle is the initial speed in the second part, where the green circle is. They're on top of each other. So if I break the problem in half, the final part of the first part is the initial part of the second part. And then we go ahead and have the ball hit the ground in a time T2, which does not equal time T1. On average, it's going faster on the second part of this journey, so don't put 1.2 seconds there. But what you can do, and you really want to recognize this, is see that the distance to fall in the first half is the distance to fall in the second half, by definition of it being halfway down. So as you look at this problem, if I throw G in here, you can see that on the red half, I have three variables, V0, G, and T1. If I use that to find delta Y1, I will then have one variable plus G, two variables, and if I can just find another variable, be it V02 or V final 2, I can then solve the equation for how far it takes to fall the rest of the way to the ground, or T2. So there's a bunch of different ways to attack this problem, including this. You can just look at the ball going the entire distance from an initial speed of 0 to where it hits the ground at some total distance, which happens to be delta Y1 plus delta Y2 at G. In fact, how about this? If I find delta Y1 and double it, I get the total distance in blue. I know G already in V0 in blue. Bingo. I can figure out the total time that it's in the air and then subtract 1.2 seconds from it. And it would behoove you to actually do it all of these different ways and make sure you get the same answer no matter how you do it. What I'm going to do now is find delta Y1, and you're about to see the whole thing pop up. So the first half of the journey, delta Y1 is 7.1 meters. I can then find the final speed at the end of the first part by doing this if I wanted to, but there are different ways to do it. And then I would know the initial speed in green, and I would have three variables now in green. I now know that delta Y2 is 7.1 meters, because it's, remember, equal to delta Y1. If I use that bottom red equation to come up with V02 along with G, easy way to find T2. So, in fact, I'm going to go ahead and do it. It's not the way I actually did it on my paper, but I'm going to go ahead and do it. And 11.6 meters per second is the speed halfway down. So then the green part of the journey, I will simply find T2, where V0 for the second half is 11.76 meters per second. Oh, darn. I don't know V2, the final speed at the bottom. So this equation that I've written in green right here won't be handy for me unless I find V2, the speed at the ground. But I can find that speed easily enough. See it here in blue? I can find that speed because in blue, I know the distance, the acceleration, and the initial velocity. So in blue, I'm going to sifu this formula, 2g delta y. Now that's the blue delta y and the blue v0, which is 0 there, so it's radical 2 times g times delta y in blue is 14.2 meters, because it's the whole distance, and that speed comes out to be 16.7 meters per second downward, and that was what would go in as my final speed for time 2 minus my initial speed for part 2 in green, divided by G, and that gives me a time T2 of 0.43 seconds. So that is T2, the time to fall the bottom distance in green. Now, notice again, though, there are different, or not notice, but there are different ways to solve this problem. You can certainly, once I know the blue V is 16.7 meters per second, which is also the green V, which is what I used it for. But you can solve for the total time the thing is in the air, going from V naught in blue to V final in blue at G, and that total time comes out to be 1.7 seconds. You can subtract the 1.2 seconds in red and get 0.5, which is close to this for the time T2. So there's a bunch of different ways to solve this problem. The time to go to the second half should be about 0.4 to 0.5 seconds, depending on rounding, how you get the answer. So here we have a pellet gun fired straight downward at 27 meters per second. The cliff's 15 meters high, so the pellet goes 15 meters downward at G. So there are my three givens. What I want to do ultimately is figure out how high above the cliff would go. So if you take a look at a pellet being fired downward that way, and you're asked, well, what would happen if I had gone that way instead? This point becomes pretty important. In other words, what is the initial speed that bullet is fired at, so I can turn it around and fire it straight up into the air to see how high it goes. Now I've plugged everything in as a positive number. I'm just going to call downward the positive direction. Remember that though, because when I come back to the green part and fire it upward, I'm going to have to call up negative, so you're going to see some of this going as a negative number. So the bullet was fired downward at 21 meters per second. So now in green, if I fire it upwards at negative 21 meters per second, it'll reach a high point where the speed is 0 in green at an acceleration downward of positive 9.8 meters per second squared. Piece of cake. Delta Y in green is V final in green minus V initial in green over 2G. Notice that my answer comes out to be negative 22 meters. That's because I'm calling up the negative direction, and the maximum height above the cliff is above the cliff. It should come out to be upward, in this case negative. Remember, pause the video if you need to. Redo the problem on your own if you need to. Try to get the same answer as me. Don't just look at my answers and fool yourself into thinking you understand what's going on. You've got to be trying this stuff on your own. So this problem kind of takes over where the last one left off. You fire it upwards. It goes 12 meters to the highest point at an acceleration of G. There's three variables in our equation. Shouldn't be very hard to figure out what the initial speed was when you launch the projectile. If you take a look at my numbers this time, I'm going to do the opposite that I did last time, just so that you can practice it different ways. I'm going to call up positive, so I make my upward displacement of 12 meters positive, but my G goes in as negative 9.8, and I come out with 15.3 meters per second. That's how fast the projectile was launched. So now to figure out how high it is when the speed is half as great, I will simply use this equation where my final speed goes in as half of the initial speed. So this is how I figure out, whoopsie, what is that going as? 15.3, the initial speed. This is how you figure out the height when it's traveling with 1/2 the speed. And that comes out to be 8.96 meters. So when it's 8.96 meters above the cliff, it's got half the speed. And then when it's 12 meters above, it actually stops. You might wonder why 8.96 is more than half of the 12 meters high, and that is because on average, the first half of the journey, it's going faster, so it ends up going farther in the first half of the journey. So 8.96 meters. All right, this is a problem that can completely jam you and is relatively easy to solve if you see what's going on. I've got a projectile, water, being launched sideways at 2.7 meters per second. And then the water is going to fall down like this. Follow a trajectory where at a certain point, I need more room on my smartboard here, at a certain point the ball just got smaller, or water got smaller for some reason. But why does the water look like a ball anyway, right? It's going to be directed at an angle that is 75 degrees below the horizontal. Doesn't look like they've given you very much. But do remember that in an XY chart for a horizontally fired projectile, Vx stays constant, that's important, and here you know V naught Y and G. So believe it or not, if you can just find the final speed of the water when it is directed 75 degrees below the horizontal, in other words, if you knew what that was, Vy at that point, you do not know what the actual speed is at that point, and you don't need it, because you do know what Vx is. Vx is still 2.7 meters per second. So this is just a little trig problem where you know one leg is 2.7 and the angle is 75. You want to find the opposite side, and the tan of theta is always opposite over adjacent. So Vy, what I'm looking for here, is Vx times tan theta. Why am I looking for Vy? Because if I can get it, I can easily solve for the vertical distance using this formula. So I'm looking for the y speed when the angle is 75 degrees below the horizontal. So just plug in 2.7 meters per second. My pen's way off here, so I'm going to write below it tan 75 degrees. And that gives you a y speed of 10 meters per second. So bring that over to this equation. I'm sorry for my sloppiness. And then you have a 10 meters per second quantity squared minus 0, the initial y speed, over 2 times 10 meters per second squared, because it's going downward. Vy and g are both downward. They have to have the same sign, and that comes out to be 5 meters. I'm using g as 10 in this part, so you know, you might, well, there is no answer given there, huh? Maybe there was on your answer sheet. Maybe it's slightly different than 5 meters because the author would have used 9.8. Okay, a rocket is fired with a speed of 75 meters per second. So I've just drawn the beginning of the problem and used sine and cosine to find V naught x and V naught y. So as we read through, the 75 is only used to find V naught x and V naught y at 60 degrees. Now, we've got an important number here, which is the wall's located 27 meters away. That tells me that my delta x is 27 meters. Now, a lot of students, when they solve this problem, are tempted to put 11 meters high for delta y, but that's not true. The wall is 27 meters away. Here's the wall, but the projectile is going to fly over it like this. So at that point, the projectile has gone sideways 27 meters, but it's not going to be 11 meters high. So don't use the 11 meters high for delta y. Happens all the time. V naught x goes in as 37.5 meters per second. I hope you immediately know, oh, I can solve for time in the x column. And I know V naught y is 65 meters per second up, and I know g. So if I can find time in the x column, I'll do that in blue here, if I can find time in the x column and stick it in the y column, I can easily find delta y, the height of the projectile, when it's gone 27 meters sideways. So I'm going to find time using the x column, delta x over Vx. That's 27 meters divided by 37.5 meters per second, and that comes out to be 0.72 seconds. You can stop and rewind this if you don't know what numbers I just put in. Then, to find out how high it is at that point, I'm going to do delta y is V naught yt plus 1/2 gt squared. Now be careful of this, because V naught y is 65 meters per second upward for 0.72 seconds. So we got to make a choice right now. What's the upward direction? Okay, we'll call it positive. Then you have to plug g in as negative 9.8 meters per second squared, or negative 10, times 0.72 seconds, the quantity squared. So what you're going to do is have a positive term of 46.8 meters and a negative term of 2.5 meters, and that gives you an overall height of 44.3 meters. That's this distance. So now you pull out that 11 meters and subtract it from the 44 meters, and the projectile is, I guess I didn't, well, we can do that in our heads. The projectile is 33 meters above the wall. So that's the final answer to this problem, 33 meters above the wall. Biggest trick in this problem is students trying to make 11 meters delta y, and that delta y just is not the case at 27 meters sideways. So There is some point the wall would be over here. There is some time at which the projectile will hit the top of the wall 11 meters high. There was a time over here where the projectile was 11 meters high. But it's the projectile, as you can see, is 44.3 meters high when it's gone 27 meters sideways. Okay, very similar problem. Here's a soccer ball. It gets kicked. It flies through the air like this. As it's flying through the air, here, let's put it at a few different places. And then it gets to its highest point, and then it starts coming back down. All right, as that soccer, and let me give me one more to keep moving. All right, so the soccer ball starts over here. It flies up. When it's here, a certain amount of time has passed. I'll call it T1, and it's gone a certain distance sideways. I'll call X1. And then when it's here, at the highest point, a certain amount of time has passed. I'll call T2. And it's gone a certain distance that I'll call delta X2. And then by the time it gets here where it gets caught by the soccer player, by the goalie, it happens to have traveled sideways a distance of, help me, 16.8 meters. And it's going sideways at 14 meters per second. So how much time, which I could call T3 or something, what is the time to get to the goalie going to be? It's going to be the sideways distance divided by the sideways speed, and that's going to be 1.2 seconds. So that's how much time it takes the soccer ball, starting here, to go up and come back down and be caught by the goalie. 1.2 seconds. And when that happens, there's a vertical speed that the ball has attained of, using these, V0y would go in as 7.5 meters per second upward. So G's got to go in as 9.8 meters per second squared downward times 1.2 seconds. One of these things has to be negative. So if we call up the positive direction and down negative, when you plug that in, this is interesting, you get negative 4.26 meters per second if you plug G in as the negative. What does that mean? That means that when the soccer ball is caught by the goalie, it's going downward at 4.26. See, when we plug G in as negative, the calculator knows that downward is the negative direction. So that's Vy when the goalie catches the ball, 4.26 meters per second downward. So to find the speed of the ball, you've got to take that downward along with the same 14 meters per second sideways, and to find the speed when it hits the ground, or caught by the goalie, excuse me, you Pythagorate the Vx and the Vy. So that would be 14 meters per second quantity squared, and when you Pythagorate, you never have to make one of them negative, because comparing x's and y's with negatives don't make any sense. X and y are never in the opposite direction of each other. So you square it anyway, so if you plug it in as a negative, I'll never know. That comes out to be 14 meters per second. That is the speed that the goalie catches the ball. What I did again was find the time to go 16.8 meters sideways, then I figured out the vertical speed at that point, then I Pythagorated the vertical speed with the horizontal speed to come up with the overall speed at that point. 39. And then lastly, I don't seem to have it here, lastly we have, let me go find it. Hello! Lastly we have the javelin throw. This is another one of these. 29 meters per second is the initial speed, and it's at 36 degrees to the horizontal. 60. Where did that come from? 36 degrees to the horizontal. Now, as that ball goes upward, I'm going to trace it out again for you. As the ball goes upward, when it gets to the highest point, remember, all it's going to have left is a Vx, which I think I have on my paper here, which is 23.5 meters per second. So when it reaches the highest point, that's all it has left, an x component. But as it goes up, the y component of 7.5 meters per second. No, sorry. I started looking back at 39. So the upward y component is 17 meters per second. Well, at the highest point, that's 0. So if I come halfway back down, or come back down, it doesn't have to be halfway. So here it is. Let me start the javelin again. As I'm going up, the x component stays the same. The y component gets smaller. It was 17. At this point, it becomes what's going to be 7.6, and I'll show you how I got that. The overall speed, which from the last slide is just the Pythagorean of 23.5, the sideways x speed, and 7.6, the vertical y speed. The amount of the speed, the black arrow, changes. Here, the overall speed's 29 at launch. The highest point, the overall speed's 23.5. At this point, I don't know it. I didn't Pythagorate 23.5 and 7.6, but it's going to come out to be about 25 meters per second. We don't need to know what that is. All I have to do is say how much time, it's on my paper, the question. How much time is required for the angle to change from 36 to 18 degrees? So that's how I got the 7.6. I used that concept once again of tan theta is opposite over adjacent. So Vy equals Vx tan theta. So the 23.5 times the tan of 18 degrees gives me the 7.6 meters per second. So that's how I got that Vy of 7.6. Now time to go from an initial y speed of 17 to a final y speed of 7.6. So let me write these for you since I just stumbled through it. The time to go from 17 to 7.6 at negative 9.8 meters per second squared is, and of course I probably actually used 10 in my calculator, 0.96 seconds. Okay, so let me talk about signs for a second. Why did I make the g negative? Because look what I did with my final speed and my initial speed. They both went in as positives because they're both up. So I got to plug g in as a negative, which is down. So 0.96 seconds is the time for the angle to change from 36 degrees to 18 degrees. Manageable 21 seconds, 21 minutes, almost 22 minutes.